Hey, everybody. Before we get started here, I have to acknowledge and apologize for the abhorrent audio quality here. I've been recently recording my lavalier mic through my phone to give myself more mobility in case I got to like walk around or adjust lights or that sort of thing instead of tethering myself to my PC. But someone was a Galaxy brain and forgot to plug in a very crucial adapter to make my lav work with my phone. So all I had to work with was not only the camera audio but scratch phone audio that was being recorded from the internal microphone, which is why you're going to hear some lovely scratching noises emanating from the inside of my shorts pocket. So that was a big brain move. Real proud of that one. So I apologize for the random noises you're going to have to endure because of that. But I'm happy with the rest of the video as is. So I didn't want to redo it all just because of one little stupid mistake. So hope this is helpful regardless of my idiocy. Welcome back to Plague Scythe Studios, everyone. Ryan here. Today, I'm going to take my best shot at, but probably not do justice, at explaining the differences between gain, compression, distortion, and how all those things play into a lot of the common vocabulary we hear when we talk about guitar and mixing music. So today's episode is actually inspired by a comment I received probably the better part of a year ago, if not further, which should give you some idea as to how backlogged I am on video ideas. But it was a relatively simple question on the surface, in that the viewer was simply asking, can you explain the details of how compression and distortion and all these things that we talk about play into one another? And it's one of those that is so fundamental to the way that we look at high-gain guitar tones in mixing music, especially guitar-centered music, that it almost sends your mind into a wormhole. But I'm going to try to do the best that I can because I think it is important to understand how all these things interact and when they are separate and how to take advantage of these as tools. To kick this off, I would start with one of the most common misnomers when it comes to electric guitar, and it's one that I'm guilty of myself because I just don't think there's much of a better descriptor that's more accurate or more concise than this, and that is high-gain amplifiers. When I say that, you immediately conjure a few images and sounds in your head. One from, maybe a 5150 or a modded Marshall tone or, an Ingle sound or something along those lines. But you automatically think of a distorted electric guitar, maybe a chuggy or hair metal band sounding kind of tone. It doesn't really matter, but you know what I mean when I say high gain. And the truth of the matter is, high gain is not a good descriptor of these amplifiers because you can actually build a clean amplifier circuit that is higher gain than a high gain amplifier. Why is that? Well, in the musical world at least, gain is a fairly ambiguous word, but when it comes to circuit design and electricity, it has a very specific meaning. So let's, for example, take a 440 hertz sine wave. Just keep it simple. An A standard sine wave with a constant amplitude, we'll just say it's 1 volt. Well, if we take this ideal voltage source and apply a gain factor of 2, that is to say we have amplified the signal, ideally, meaning we don't introduce any other artifacts or things that we don't want yet, then we'll now have a signal with an amplitude of 2 volts because we have doubled the amplitude. That is how ultimately you calculate gain. In the musical world, we almost never talk about gain as a straight factor, and though it's more common in circuit design and electrical engineering, generally we convert those units into decibels, which is basically an operation of log 20 and comes out to roughly 6 dB being equivalent to 2 times gain, and 20 dB being equivalent to 10 times gain. So if I were to add 6 decibels to a signal, say in my audio workstation program, then I've essentially made that signal twice as loud. And you start getting into some different calculations when you talk about power or loudness, but for the sake of this simplified explanation, if I say the signal gets twice as loud, then take that as meaning the signal has twice as much amplitude. So that's where we end up getting the units of decibels. That's why you see on a mix console, or perhaps in the output settings on an effects pedal, especially those of the digital kind, you'll see level measured in clean, pure decibels. So if gain measures the clean amplification a signal undergoes, that must mean a high gain amplifier really amplifies the hell out of a clean signal, and it undergoes an insane gain factor, so many dBs. And especially eclipses those of a clean circuit. And that's part of the story, but that's not all of what's going on. In fact, under ideal scenarios, and even some actual amplifiers out there can amplify a signal with a higher gain factor and never turn into a high gain amp in the way that we think of. It will be simply louder than those high gain amps, but still remain clean. So what are we actually saying when we say high gain amps? Well, in short, we're just trying to say this amp has a lot of distortion on tap. So we really should be calling these amplifiers high distortion or high saturation or something other than high gain, because it doesn't tell the entire story. Now, when I say the word distortion, most of you immediately have a sound in mind. You know what I'm talking about. In comparison to a JTM 45 on lower volumes, a JCM 800 has far more distortion on tap, and a JCM 2000 even more still. But how do we quantify or even qualify distortion? Like basically all of today's concepts, distortion is a big umbrella with a lot of things that fall under it. But to keep it relatively simple for now, we'll say that distortion is any operation that gets applied to a signal waveform that does not fall under the category of clean equalization, clean amplification, or clean dynamic range manipulation. A lot of shuns there, but follow with me here. I got a couple examples here on the screen. So this is a comparison of a guitar DI and the result when you reamp it through a guitar amplifier preamp and a common overdrive pedal. So both of these are examples of distortion. They both actually have asymmetric distortion, where one side of the waveform is behaving differently than the other. Both the preamp and the pedal are amplifying the amplitude of the incoming signal, but do so in very different ways. They don't really resemble each other visually. They certainly don't resemble each other sonically. You can see the frequency content difference, how they've generated different harmonics. And you can also see there's not an obvious relationship between the incoming signal amplitude and the resulting amplitude on this waveform, which is something else we'll get to in a bit. This is where we have to start talking about the concept of thresholds, or what is often referred to as headroom, and clipping, which is a result of running out of said headroom. In an ideal circuit that I was talking about earlier, if we apply, 100x gain, then we make that amplitude of the incoming signal 100x louder. That's all that happens. We increase from, say, 1 volt to 100 volts in that previous example. But we don't live in an ideal world, and as it were, for preamplifiers and a lot of our effects units, they are designed to intentionally not allow that much amplification, or at least clean amplification, whether we're talking about the tube gain stages and 2203, or the clipping diodes and a tube screamer, or the multiple transistor gain stages and a fuzz pedal. What we ultimately hear is a circuit running out of headroom. For a simple visualization, let's say that my Mike St. John Devin Townsend project pick is the leading edge of a sinusoidal wave, and the edges of my monitor here are the physical limits that this circuit can handle, or the threshold before we start running into clipping and distortion. So under the threshold, the circuit doesn't care. If you give it a signal this big and you amplify it to this big, it's still going to remain that same sort of signal. But what happens when you start feeding a circuit too much gain? You start to overdrive it to where theoretically you should be pushing up here in amplitude. Well, we've gone past the physical limits, so Mike St. John's going to start riding the edges, and it's going to start clipping off the edges of those waveforms, and that's where we literally get the term clipping. You will quite literally see the highest and lowest points of the waveform clipped off, which is where we get the term hard clipping. There's some hard clipping pedal designs you might be familiar with, like a Proco Rat or an OD250, or many of these spin-offs that have been recreated in the modern day, but that is just one kind of clipping. In fact, there's also soft clipping, which you may be familiar with something like a tube screamer or a blues breaker or a super overdrive, where instead of just grinding the edges of the threshold, so to speak, it tries to miss it, tries to avoid it, but it's still distorting the waveform. And this is a sound that we hear and is often tried to be replicated when it comes to tube preamplifiers. And that is one of the many reasons that the pedal market even came to be in the first place, with a lot of these designs attempting to replicate the sound of an overdriven tube preamplifier, or even a tube power amp in a lot of these cases. Of course, clipping isn't quite that simple. not only do you have hard clippers and soft clippers, but the threshold on each side of the waveform isn't necessarily going to be the same. So oftentimes tube amplifiers are associated with having asymmetrical clipping, especially of the Marshall variety, which sounds more aggressive and oftentimes more harmonically rich and full to our ears. When it comes to hard clipping specifically, or making the highest and lowest points of a signal completely flat, well, that actually cannot exist in the analog realm. You can get really close, but there's always going to be some amount of overshoot or undershoot because you can't make a right angle or damn near a right angle when it comes to an analog signal. So you get some interesting behavior when you try to make a square wave in the analog domain, and that's oftentimes why you see high gain amplifier signals look something like this, or high gain hard clipping pedal signals looking something like this, where there is a lot of manipulation going on with the transient and with oftentimes high frequency or low frequency content being attenuated to influence the tone. So a lot goes on when it comes to clipping and distortion. And I suppose that's why there's so much confusion when it comes to defining what distortion really is in musical applications, because it can be as aggressive as a spitty gated fuzz pedal. It can be, an overdrive pedal. It can be a high gain amplifier, or it can be as subtle as the color that an otherwise passive equalizer circuit adds to a mix. A lot of people would run through, like a Pultec EQ, back in the day being a real outboard equalizer circuit, or oftentimes emulated with VST plugins now, not because they're exactly trying to do anything with the frequency spectrum, but because they like the sound that the tube amplifier circuits are adding. Even though we're not trying to increase the amplitude of that signal or change any of the frequency content, there is still some imperfections in the circuit, whether it be the saturation of the transformers or what the tube amplifier portion's doing. There is something being added, some slight amount of harmonic content being generated that fills in those sonic gaps that we feel is empty otherwise, or especially in the digital age that we feel is not being replicated properly with software or by cleanly recording something. Most mix engineers nowadays apply some sort of saturation plugin either on elements of the mix or the entire mix chain to emulate a lot of the sounds we heard in the old days, because there was no such thing as a perfectly clean signal chain. So, when we listen to a digital mix compared to things that were recorded 30, 40 years ago, then we start to miss those subtle elements that the analog console added, or the tape saturation and all the weird mechanical things that offered. So we have tape emulation plugins, we have tube emulation plugins, just straight up distortion saturation plugins that add that harmonic complexity and some of the very light overdrive that we don't even pick up on as distortion, but it's there. And we hear more as just adding body and complexity to an otherwise, what could be considered a sterile sounding mix. Us guitar players out there can think about it from the perspective of a clean tube amplifier. Sometimes a totally clean, like DI, straight into a console, or like completely digital signal chain sounds really good for cleans. And if you're going for that pure sound, it can be really good. But I think for a lot of guitar players, we prefer to have that edge of breakup, just a little bit of that spanky, Fender 6L6, slightly hot kind of clean tone, where there's something there. It's not necessarily, overdriven or distorted, but there is some amount of complexity that, again, fills in the gaps that wouldn't otherwise be there. And when you compare it to a totally clean transistor amp or, straight into the console sound, those might sound a little sterile by comparison. Clipping and distortion also has another common use in especially contemporary music production that has very little to do with tonality and frequency response and more to do with loudness. Because as you might be able to see even from this visualization of pedals and a guitar preamplifier, the more you clip a signal, the more that the signal spends time at the maximum threshold. So, if we have a threshold of 1 volt and we've got a sinusoidal wave that has an amplitude of 1 volt, but we double the gain, and now we're clipping for a lot of that signal, what's actually happened is the signal is louder. The signal may never actually trip that 1 volt threshold, but it spends more time there, and through the persistence of that signal, we hear it as being louder, which has thereby decreased the dynamic range of that signal. Which begs the question, what is dynamic range exactly? Well, if we look at our sinusoidal wave example again, you can see that there's some parts of the signal with higher amplitude than others. You might have one that's, halfway up this picture, some that are, barely tripping 10% of that amplitude. Well, if we wanted to decrease the dynamic range of that, we would want to bring the amplitude of the highest peaks down closer to the lowest peaks. And this is where we get into compression. For your run-of-the-mill compressor unit or VST plugin, meaning it does nothing else to the signal except just compress, you'll often find some common controls exposed to the user. Sometimes they're hidden, sometimes they're baked into the circuit, but for ones with more or less everything exposed to the user, you'll see a threshold control, just like the threshold we talked about with distortion, where anything above that threshold, instead of being clipped, gets attenuated. So, say you have a threshold of 0.8 volts, well, then that 1 volt signal will get attenuated to 0.8. It does not make the entire signal quieter, it just makes that peak quieter. The ratio controls how aggressively the compressor attenuates the signal that goes above the threshold. So, 2 to 4 to 8 to 1 all describe how powerful of compression you're experiencing, with something like 20 to 1 being really extreme, and infinity to 1 basically being a limiter, which will not let any of the signal over this threshold, at least in theory, if it can catch it in time. Which brings up the attack and release controls, which determines how fast the compressor reacts. It's going to be, on the spot and catch every little peak and react to every transient, or is it going to take some time to recover after, 3 or 4 periods of a waveform or even longer? Oftentimes attacks and releases are set rather quickly in mixing scenarios, though depending on just how aggressively you want to attenuate a signal or compress the dynamic range, you might want to set them a little more in the 100 to 300 millisecond range. It really depends on what you're trying to do. An expander is the same thing as a compressor, just in reverse, where any signal that falls under that threshold will be decreased in output level. So this is where you would want to expand a signal or increase its dynamic range. And there's some applications where you might want that, where you may want to highlight the hits of a cymbal and then back down afterwards to make more room in the mix, where you don't just have a blanket of high frequency content. You can also achieve the same thing with something like an envelope shaper. But that's all to say that dynamic range manipulation is a very important part of the mixing and mastering process, and is even something that we often take advantage of, whether we mean to or not, on a solo instrument level. So all of that is assuming that whatever compressor we're talking about is just that, a straight up compressor that does nothing else. It is ideal in every way. It's not introducing anything else to the signal. But when it comes to analog units and a lot of the plugins that emulate those analog units, they have all of their little imperfect circuitries as well, whether it be, again, transformer saturation or the amplifier circuits that are in them. So even the most transparent analog designs, depending on whether they're the VCA or optical or tube variety, can indeed add their own version of overdrive and mild harmonic distortion in ways that we like. And distortion and compression, when you start mixing the two, things get really complicated, but really, really interesting. So coming back to our amplifier and our pedal situation here, you might have already picked up on this, but as you can see, as the distortion level is turned up on this pedal, not only does it gain a more hard clipping profile, but the differences between the lowest amplitude peaks and the highest amplitude peaks start to decrease. So by adding distortion to the signal, by spending more time near the threshold, we've actually decreased the dynamic range of this signal at the same time, even though we didn't even really mean to. So that is why oftentimes we talk about high gain amplifiers or distortion pedals or overdrive pedals as having some quality of compression to them, where, no matter what you do to it, you kind of get the more or less same reactivity out of it. Now, we don't want no reactivity. We don't want infinite compression on a tube amp. You want to hear the transients of your pick attacks and be able to react to a player. But some level of compression is a good thing. It's something that we look for in all kinds of music equipment, whether we're consciously going for that or not. Because if we just listen to a raw guitar signal, it would be pretty unwieldy in a lot of the genres we use it for. In that prior example of the mix engineer using a clipper plugin to make a mix louder, that is essentially altering the dynamic range. You are making the mix spend more time at that threshold and thereby being louder all the time. Now, it's not the same as rounding out the signal like a limiter or a compressor would, and once it gets translated into the analog domain, you hear some interesting results of that. There's more transients, it's punchy, and it's just a bit of a different sound, kind of more aggressive. You don't want to go too extreme either way or you run into problems, but a happy medium between the two is generally what we hear in a lot of contemporary music. Now, one thing I've not mentioned up to this point is that compression and especially clipping all lowers the amplitude of the waveform, so you have to make up for that gain later on, which is why you'll see compressors with a makeup gain control, oftentimes a auto makeup gain control. Same thing with a lot of these clipper plugins, and that's how you get the loudness after the fact. So how can I succinctly wrap up such a convoluted episode of Explained? Truthfully, I don't know. I don't know that it's possible, but if I had any advice, I guess it would be, one, realize every move that you do has some elements of everything to it, and it's going to interact with each other. And two, be very intentional about the moves that you're making. Don't get me wrong, experimentation is great, and that's what leads to some really cool, gnarly guitar tones and mixes, and sometimes intentionally doing something you know is wrong is that, perfect secret ingredient that no one else has. But, realizing that a high-gain guitar amplifier is already going to be pretty compressed, so you a lot of the times don't even need to add a compressor to a guitar bus. Sometimes you just need to, handle the palm mutes, and a multiband compressor in one little area will take care of all your problems. You don't need to over-compress a bass or add too much distortion to a vocal line or whatever it might be. Be very intentional with these things, especially when we talk about a mixing application, but even when it comes to the instrument level as well. Sometimes the difference between horrible and the best thing you've ever heard is just a little tweak of a gain knob, either on a guitar amp or in your audio workstation program. Sometimes what you try to do to fix things introduces more problems than it solves. We didn't even get into like phase shift when it comes to equalization or some of the other interactions that compression has with equalization and distortion. But in general, everything that solves a problem has a drawback, especially when it comes to the musical side of things. So just keep that in mind. Don't be afraid of it, and realize that it's all related. And the vocabulary for music production and guitar playing is just screwed. But we try to get by, don't we? Anyhow, if you have any other questions or comments, please leave them down below. Thanks very much for watching, and we'll see you next time. Bye.